Alright, so hopefully you've been checking your email and you know that we aren't having regularly scheduled class on Friday, the October 26th. I do want to say that I will be on campus today, but I won't be able to talk a lot, so that's why I'm making a couple more videos here um, to keep us moving through the course, just to kind of give a plan for what's going to be happening here in these next few days. I haven't really received many questions on the homework, so what we're going to do here is on Monday, and let's see here, let me do some basic arithmetic here. Saturday's the 27th. So on Monday, the 29th, uh, we will go over homework. Now, if we don't have any questions on the homework, of course, we will continue on with new material. Now, the homework you should be focusing on would be homework from 4.1, 4.2, and 4.5. I'm going to start this. We are skipping 4.3. So we will never cover section 4.3 in this chapter, so obviously it won't be on your exam or any quizzes. Speaking of quizzes, we're going to have a quiz on Wednesday, October 31st, so happy Halloween. For sure, 4.1 and 4.2 will be on the quiz. Maybe 4.3. I haven't 100% decided that. I'll let you know on Monday. I will tell you, just because of things the way they've been going here, what I've decided to do for this quiz is that I will allow you to work in groups, but no more than 2 people per group, and you don't have to work in groups. Some people prefer to just work on their own. That was the case for me when I was in college. But you are allowed to work with someone in a group, no more than 2. And if you do work in a group, put both your names on the quiz that you're going to turn in, and I will only grade 1 quiz between the 2 of you. All right. So let's see where we're at here. So what we've been doing here, let's just kind of recap some things here. So 4.1, we talked about extrema, and we had the critical numbers, and we had our first derivative, not first derivative, that's the next section. We had our absolute extrema, which, remember, we used the extreme value theorem for this. Make sure you know the extreme value theorem. You can be guaranteed this is going to show up on the quiz next week, as well as on the next exam. Absolute extrema, and then we had relative extrema. And those were the main topics from 4.1. 4.2 really dealt with increasing / decreasing and concave up / down. And we did intervals of, I'm just going to draw arrow going up, arrow going down for increase and decrease. We did intervals of concave up, concave down, and then we called these here, we gave them fancy name, the first and second derivative test. for relative extrema. Okay, so that's where we kind of are at here. As I said, we're skipping 4.3. 4.4 now, which is what we're about to start here, is optimization. Now this is a section that most people tend to not like, and I think the reason they don't like it is it's essentially just story problems. But we really shouldn't be intimidated by this section. I know people don't like story problems, but the reality is when you get into the workforce, they're not going to be written like the story problem, but everything you're doing in the workforce is a story problem. You have a set of conditions or specifications, and you've got to meet it. Now, the difference is in the workforce is that they're not these contrived examples like we have in a mathematics textbook. They're obviously, quote, real-world applications. So let's go ahead and look at how we do optimization. So first off, I mean, I don't like writing procedures down necessarily a lot, but first off, what I like to do here is always, the first thing I like to do is determine what I am optimizing. The reason I like to determine that is it gets me a starting point on any equations I'm going to have to write down. Because I'm going to have to develop equations in all these story problems. No equations are typically going to be given to us. So determine what I am optimizing. That's the first thing. And then either highlight or mark key information. Most of these problems are going to benefit from a picture drawn, so draw a picture. Label that picture. And then write down equations. Keeping in mind what you are optimizing. Now this next step here is one that sometimes people struggle with, is you have to obtain an equation with a single variable. Because we are only doing derivatives with one variable. Many of you, not all of you, will take Calc 3. When you get into Calc 3, you'll talk about doing derivatives and integrals with multiple variables. It's not as difficult as it might sound. Obtain an equation with a single variable. Optimize equation. In other words, when we optimize, we're going to find the critical numbers. Verify critical numbers are max or min. If you don't actually verify that there are max or min, we don't actually know which one we're going to have here. So there's a story back in the day that I don't know how true this is. It's been passed down, you know, the telephone game, but that basically NASA engineers were trying to create better fuel burning efficiency for rocket fuel. And so, you know, there's different formulations of rocket fuel or just fuel in general, right? So you want to get the most efficient burn out of that, get the most energy out of it. Well, they had these complicated equations, not like a simple one like what we're going to be dealing with in this course, but complicated equations, multivariable calculus. They optimized it, found their critical numbers, and they said, that's our answer. And so then when they mixed up this rocket fuel, now this wasn't, they didn't put this on a ship yet, they went in the test lab and started testing this rocket fuel, and the performance was horrible. Just absolutely horrible. None of it made sense to any of them until finally someone realized that they actually hadn't found maximum efficiency, they had found the minimum efficiency. They had found a fuel mixture that gave them the minimum efficiency out of that rocket, out of those particular components to make that rocket fuel. So that's why we have to verify critical numbers of max or min. You can't just assume that because you found a critical number, you've actually optimized the problem. Now, in these problems, of course, we will have been able to optimize them, but what happens when you don't? Well, there are some times where you can have problems where there are no optimal solutions. That's the real world. It's like sometimes you have to, pick the worst of two bad choices, or the best of two bad choices. So we always have to keep that in mind. All right, so let's start a first problem here. So we have a piece of cardboard. (14 inches by 10 inches). Oops, that's the wrong thing here. Sorry about this. My tablet sometimes goes a little wonky when I hand, touches other areas on the screen and goes a little wonky. So we have a piece of cardboard, 14 inches by 10 inches. We cut out corners and fold up the sides I should make one more adjustment here. It's not just cutting out the corners, we cut out square corners. And fold the sides up to form an open top box. What are the dimensions that yield the largest volume? Man, I'm just struggling less here with this. Going back to the main screen. I think it's my wrist keeps hitting the home button at the bottom of my screen here. Alright, so first thing, what are we optimizing? We're trying to maximize volume. Says so right in there. What are the, well, I forgot the R there. Well, what are the dimensions that yield the largest volume? We're trying to maximize volume. So we're looking for a maximum. Now it says draw a picture. Now, how accurate these pictures are isn't necessarily the importance here. What it is that we get an idea of what's going on. So I've got a piece of cardboard here. And this is my piece of cardboard. And it's 14 inches by 10 inches. So I'll make the shorter side 14 and the longer side, shorter side 10, longer side 14. And then I'm going to exaggerate these little cutouts maybe. I'm going to cut out little squares here from each of the corners. And then I'll put little dotted lines here, because then I'm going to fold them up on these dotted lines to form a box. An open top box. Now you could draw that 3D perspective. I'm not going to bother doing that. I think we can all visualize what's going on with that. Well, let me go ahead and take a real quick stab at it. So wasting time on this video trying to draw this box here. Alright, so there we go. Not bad. But fold up the sides and we get a box that looks like that. Great. Now we should label some things here. Well, first off, let's just go ahead and label. I'll go ahead and label it on the box here. So let's call this the length, the width, and the height. So we're going to be going back and forth between these pictures and the actual equations here. So we know that volume, we have a very simple equation for volume because that's what I'm trying to maximize. It's equal to length times width times height. Now the problem is I'm trying to get an equation with one variable, and there's three variables there. So let's go back to this other picture here and label some other things here. So I'm going to label the sides of these squares as x. You can label it anything you want to, but I'm going to label it as x. And then I'm going to highlight something here. This green piece right here that I highlighted, I know the dimensions of that because I'm cutting out x from each side. So this is 14 minus 2x. And then if I look at this blue side right here, I can do the same thing, except in this case, this would be 10 minus 2x. So now I can actually write here that my volume is equal to, well, my length. It doesn't really matter which one you label length, but just because of the way I have it labeled in these pictures, my length would be 14 minus 2x times width would be 10 minus 2x. Height is just x. So now I have an equation for my volume, but I only have one variable in it. This is ideal because now I can go ahead and write a single equation here, take a derivative and everything. Now before I take a derivative of this, though, I really want to multiply this out. And I haven't actually worked this problem out, so I'm going to just take it a couple steps here to FOIL it out here. So that would be 140 minus 20x minus 28x. I really need you guys here to make sure I don't make a silly mistake. Plus 4x squared times x. And then what do we do here? Whoops, that's not the derivative. That's just multiplying it out. So we have that the volume is equal to, and I'll go ahead and write in descending order, 4x cubed minus, so that would be 48x squared plus 140x. Alright, so that's my equation. Now I'm ready to optimize. So honestly, on these problems, this is the hardest point to get to. Once you get to this point, it's the exact same process for all of the problems. So what do we do at this point? Well, what we do is we take a derivative and find my critical numbers. So v prime would be 12x minus 96x plus 140. And so I need to set this equal to 0. So 0 is equal to 12x minus 96x plus 140. Gosh, I can't take derivatives. 12x squared, you probably already all caught that. So let's go back here. Derivative would be 12x squared minus 96x plus 140. Set that equal to 0 to find my critical number. So then I would just use the quadratic formula or factor it. This doesn't going to factor very nicely, but if you use the quadratic formula, I'm not going to write it down here. We should all know the quadratic formula. You get two answers, 1.918 or 6.0 Now, I claim one of these doesn't make sense. Now, if we think about it for a second, we should be able to see which one doesn't make sense. And I claim this one doesn't make sense. And why doesn't that make sense? Well, let's look back at my volume equation. I've got 14 minus 2x. Remember, that was my length. And then I've got my width being 10 minus 2x. But if I had 10 minus 2x for the width, and x was 6, that would mean my width would be like negative 2. But that doesn't make sense at all. So that clearly can't be one of the ones that I'm interested in, because that's not giving me a box at all. I'm just cutting apart a bunch of cardboard. So clearly x equals 1.918 is the one that I'm looking for. But now we have to verify I like to use the black here. Verify x equals 1.918 is a maximum. Now there's two ways to do this, and we'll do it both ways. There's the first derivative test. Now I'm not going to do it both ways on the other examples we're going to look at. I'm just going to do it on this first one here. The first derivative test, well, that means what you need to do is you need to look at your number line here. And we need to put our critical point here, 1.918. And then we need to pick something to the left of the critical point, something to the right. Now you want to be careful, left and right, you want to make sure that you avoid any other critical numbers, even if they're in areas that don't make sense. So I don't want to pick like 10, because that would be on the other side of this critical number that I know is bad. So just pick numbers that are close. I mean, I would probably do 0 for this one just because I'm fine doing 0. So if I do v prime at 0, I would get v prime at 0 would just be simply 140. But again, the key thing is it's positive, so that means I'm going up. And then I would probably just do v prime at 2. I mean, that's bigger than 1.918, and so this would be 12 times 2 squared minus 96 times 2 plus 140. And I'll do that real quickly on my calculator here. And you get that this is equal to negative 4. And so that means I'm going down. But I'm going up, and then I'm going down, so clearly that means this is a maximum. Now the other way to determine it is a maximum is to look at the second derivative test. And remember, with the second derivative test, as the name would imply, you need, of course, the second derivative. So v double prime, let me scroll back up a little bit here. Here, let me write v prime down again, because that's the downside to some of these tablet screens, is I don't have a huge board to keep referring back to other things. So v prime was equal to 12x squared minus 96x plus 140. Alright, so that's what v prime is. So v double prime is equal to 24x minus 96. Then remember, with the second derivative test, we plug in the critical number. So I want to do the second derivative test at 1.918. And so this would be 24 times 1.918 minus 96, which I already know that's going to be negative, but let's go ahead and compute out what that is. So I'll punch it in my calculator real quickly, if I can punch it in correctly. And we get that this is equal to negative 49.968. And the key thing is that's negative. But now I'm dealing with second derivative, and second derivative gives me concavity. So negative means I'm concave down. but that means the critical number, which is going to be sitting at there, my horizontal tangent line, well, that's clearly a maximum. Now, you don't have to do both the first and second derivative tests, but you have to do one of them to verify that you found a max or min. Now, here comes the mistake that a lot of people make on these problems, and it's a silly mistake, and it's frustrating to lose points over this. You've done all this work, you've verified that you find a maximum, and then you just move on to the next problem, and you lose some points. And the reason is you haven't actually answered the question. I'm going to scroll back up here. It says, what are the dimensions? So I have to know what the dimensions of the box are. Well, we know that the height is just this critical number. So the height is 1.918 inches. The length, or I'll just do the width for some reason, is 10 minus 2x, which would be, plugging in my calculator here, 6.164 inches, and then my length is 12 minus 2x, which again, plugging that in, is 8.164 inches. And so that would be the actual answer, because I got my height, my width, and my length. Now, you can write it, if you want to write it as something like 8.164 inches by 6.61, not 6.61, 6.164 inches by 1.918 inches. That's fine to do as well, or you could leave it like this. Alright, so this video is much longer than I normally make them, but we did get through one example here. We're going to for sure do at least one more example with optimization, maybe two. And then just to remind you, we're going to have a quiz next Wednesday, and Monday we'll have opportunity to go over homework questions.